Good morning, everyone. So today we talk about chapter 10, the material nonlinear analysis. And the material analysis is a very important part of the finite element analysis. Besides, whenever you do the finite element analysis, you have to pick the material for model for your material, and to do this you have to you need to have a lot of knowledge in order to pick or in order to define the correct material model. And so in this chapter we will talk about the material model. We will talk about different material model, but this cannot cover all the knowledge. So in order to know more, you have to read more books, and you have to do more practice, and you have to keep learning. Okay, so in this chapter we will cover three parts. First is the material nonlinear problems, and we will cover nonlinear elastic problems, elastic plastic problems, material yield criteria, and the material hardening rules. Second, we will quickly go through the FE analysis of material nonlinear problems. And third, we will use a typical example, the visco hyperelastic skeletal muscle material, as an example to show you or to demonstrate the material nonlinear analysis in ANSYS. So first part, the nonlinear material. Let's have a look. What is nonlinear material? So the structural nonlinearity is caused by the nonlinear stress-strain relationship. So material nonlinearity means the stress-strain relationship is nonlinear. Okay, so this is a typical stress-strain curve for the steel, and we say for the steel that the initial part is linear. So the material nonlinear material is if this is the stress, this is the strain, and it is a nonlinear curve for the stress-strain relationship or for the constitutive relationship. Okay, and the nonlinear elastic problem, the stress-strain relationship is nonlinear, and the relation is the same during loading and unloading. Okay, the relationship is the same. So during loading and unloading, so which means we don't have the visco effect. An example of this is the hyperelastic material. So for example, for the hyperelastic material, the stress-strain relationship is the nonlinear. And if we do the unloading, it will follow the same path when we do the unloading. So if it's this kind of behavior, then we call it hyperelastic material. And then it's the elastic plastic problems. We know this is a typical curve for the steel. So we have the linear part. Then after yield point, the material goes to the plastic region. So this is the plastic region, and then at one point, then it becomes the necking effect. Then the curve will drop, and then at one point the material is filled, and then the failure, and then the stress reduced to zero. Okay, so this is the elastic plastic problems. So we have the elastic, and then we have the plastic. So for the elastic plastic problem, the strain not only depends on the current stress, but also along the loading history, and the stress and strain is not a one-to-one mapping anymore. Then let's have a look at the hyperelastic material. The hyperelastic material is also very common in our world. For example, the rubber. Okay, and for example, also the biological material like our soft tissue, like the skin and the muscle. They all have hyperelastic material. So the hyperelastic material, well, let's see the definition. The hyperelastic material are the elastic material that the work is independent of loading paths. Okay, so which means if we loading in different paths, they will have the same work. So the work is independent of loading paths. If it's have exhibit this behavior, then it's hyperelastic material. And the constitutive relationship of hyperelastic material are derived from the strain energy density function. So we know for the material, the very key part or very important part is to derive the constitutive relationship. That is the constitutive model. Once we have the constitutive relationship for the material, and then anything else is solved. So for the hyperelastic, it's derived from the strain energy density function. So therefore, we need to work out, we need to write out the strain energy density function for the hyperelastic material. And for the hyperelastic material, there are several subtypes. So the first is the incompressible new hooking material. Okay, incompressible new hooking material is a type of hyperelastic material. The second is the compressible new hooking material. Compressible. Okay, so this is a incompressible, which means the Poisson ratio equals or approximately equal to 0.5. Okay, this is incompressible. And this is compressible. This is compressible, and the compressibility is controlled by this parameter. We sometimes we call it the compressibility factor or compressibility material. And then we have the compressible new hooking material. Compressible new hooking material. So for the compressible new hooking material, then we have those additional terms to control the compressibility of the material. Okay. We have the incompressible moniriveling. So this is here is the new hooking material. The feature of new hooking material is they only related to the first environment. Okay, they only related to, or only have the relationship with the first environment. Okay, and this is the Jacobi matrix. If you are not familiar with those, please read the relevant books. This is the definition for the first environment. This is the definition for the Jacobi matrix. And the moniriveling material is more complex than the new hooking material, and it is also a kind of hyperelastic material. So, and it also have two types. We have the incompressible, we have the compressible, and for the incompressible, when we say moniriveling, they different as the new hooking. It has a relationship with the first environment, but also with the second environment. And this is incompressible. And for the compressible material, they have we should have this additional term. This is the compressibility factor. Okay, and for the compressible material, we have also the first and second first and second environment with the volume change eliminated. And with this we have two terms. We have two terms, but we can have more terms. And so if we have more terms, we can derive the more terms moniriveling material from this generalized material model, from this generalized equations. And then we have here we say we have the incompressible and the compressible, but there's another case which we call it quasi-incompressible, which means it's nearly incompressible material. And for this kind of material, we have this is the strain energy density. And for this kind of material, we just need to make d1 very small. So d1 very small, which means 1 over d1 is very large. So it's very large, so which means the Jacobi determinants J should approximately equal to 1. J approximately equal to 1, the physical meaning is it is incompressible. So by setting this parameter, we are making the material quasi-incompressible. Okay. Then we have the incompressible isotropic hyperelastic model. So this is the incompressible isotropic hyperelastic material model, and in those model we have the definition for the first invariant, second invariant, the third invariant. This is the invariant with the volume change eliminated. And we have several other types of hyperelastic model. This is quasi-incompressible transverse isotropic material. So we in chapter 2 we have introduced you the concept of transverse isotropic material. What does the transverse isotropic material means? So a typical illustration or explanation is this figure. So we have this is the fiber enforced. This is a transverse isotropic material. So we have the fiber in one direction. Therefore, the mechanical behavior in the fiber direction is different as in the cross-section plane. Okay, it's different as the cross-section plane, and we call this the transverse isotropic hyperelastic material. So to write out the strain energy density for this kind of material, then we have to introduce the fiber direction, which is I4 here, and so we have the incompressible transverse isotropic hyperelastic model. So and the strain energy is written as this. So we need to introduce, or we need to describe the fiber direction, or we need to introduce the fiber into the strain energy function. So this is I4. This is in relationship with the fiber. And we said the hyperelastic material, for the hyperelastic material, the strain energy, the strain stress strain, or the constitutive relationship is derived from the strain energy function. And so we write out the strain energy density, then we follow the standard step, the standard procedure to work out the stress, which is to work out the stress and the strain relationship. And the procedure is we have the strain energy function, then we derive the polar Kirchhoff stress. This is a relationship with the strain energy function. And then from the polar Kirchhoff stress, we work out the Cauchy stress. Okay, this is Cauchy stress. So it is step by step. It is the standard procedure. Okay, and if you don't understand, you can find out this procedure in many books, and you can read those books. Okay, so this is the hyperelastic material. It's a kind of nonlinear material, and whenever you want to simulate those hyperelastic material, for example, the rubber, you have to, in the FE code, or in the FE software, you have to, usually people, they ask you to give those values like C1, C2, and the K, or here like the fiber orientation N. So don't be confused why you have to give those. Okay, because that's the reason is because once you give those the value for those parameters, and then the program will put them into those formula, and then they use the formula to derive the stress strain relationship. Okay, that's the theory behind those GUI operations. Okay, then the second type is the elastic plastic model, and this is more complex because we have the plastic deformation involved. So, and this is a typical elastic plastic material curves. So we have the elastic, as we already mentioned, we have the elastic, then we have the plastic, then we have the linear. Okay, and let's say when you meet this kind of material, how do you simulate it in the FE? How do you define the material model in the FE program? Okay. So let's first have some basic concept to prepare you for the FE part. So in the engineer problems, the ideal plastic model or the linear hardening model are used. Okay, and the main parameters are only the yield stress and the elastic modulus and the hardening modulus. Okay, so this is an ideal plastic model. This is a stress hardening. So which means after the yield point, the stress is increasing. This is stress hardening, and this is a stress softening model. So here you have the yield point. Of the yield point, the stress is softening, is decreasing. So this is the stress softening model. Okay, so we have 3 different types of model, and for the real engineering problems, usually you have sometimes you use one of those models to simplify the mechanical behavior of the material, and how to simplify it and why you simplify it. And this is a tough question, and this will depend on the specific application. So, and then we have the plastic mechanics here. Mechanic here is a separate course. Okay, we don't cover all the knowledge, but we cover some important part. We cover some part related to the FE. Okay, the plastic mechanics. The state when the material starts plastic deformation. Okay, plastic mechanic is dealing with the state when the material starts the plastic deformation. For isotropic material, the yield function is like this. It's the yield function, and here F0 depends on the material type, and it's called the yield function. Okay, this is called yield function, and F0 equals to 0 represents yield surface. So we make it as a function, and then we draw it, and then this is our yield surface. Okay, and then there's different types of yield criteria. This is similar to like we from the fracture mechanics course. We know we have different criteria for the fracture, and for the plastic mechanics we have different criteria for the yield. The yield is when you above this criteria, and then the material goes to the plastic state. Okay, and we need to, for different material we have different criteria, and that's why we have many different criteria. So let's go through each of them and see what's the difference, what's the definition for each yield criteria, and what's the difference between them, and for a specific material, which yield criteria should we use? If we use the wrong yield criteria, then the mechanical behavior or the model is used will be very different, and you cannot accurately simulate the mechanical behavior of the material. So first, let's have a look at the Van Mises yield criteria. So the Van Mises yield criteria is used a lot, and even is used for the fracture criteria, and it's applied for the ductile material such as metal. So for example, if you want to judge whether the metal has gone into the plastic deformation or not, you have to check the Van Mises stress of the metal and to see if it's above the yield stress or not. Okay, so let's have a look at the definition. The material start to yield when the second derivatoric stress invariant or the Van Mises stress reach a critical value. Okay, and this is the definition for the Van Mises stress. And this is the definition in terms of the principal stress. So because we know those are the stress components. Those are stress components. We know those stress components, 6 stress components can be transformed to the principal stress. Therefore, we can write the yield stress or the Van Mies stress in terms of the principal stress. And this is under the uniaxial loading scenario, which is the most simplest case. So on the uniaxial loading scenario, we only have the stress in one direction. So the Van Mies stress is equal to sigma 1. Okay, so this Van Mies yield stress is we have to remember it. It is be used to check material has gone into the plastic deformation or not, and is used for the ductile material and is used for the ductile material. Okay, and here is a plot of this function. Okay, it's a plot of those functions. So, and the circle, you see the circle here is the Van Mies yield surface. Okay, the circle is Van Mies yield surface. So this represents a circle. Okay. And then the second yield criteria. Okay, the Transcar yield criteria, and this is also applied to the ductile material. Okay, it's also for the metal, and it's also for the ductile material. Okay, then we should know what's the difference between the Transcar yield criteria and the Van Mies yield criteria. So the definition for the Transcar yield criteria is the material start to yield when the maximum shear stress reach a critical value. So we judge by check the maximum shear stress. Okay, and the formula is like this. We obtain the shear stress and we check it with the critical value. Okay, we check with the critical value. So this is our Transcar yield stress, and we check if it's reached the critical value or not. If it has reached critical value, then the material has started to yield. Okay, and then again we plot those equations in the diagram, and we say this is our Transcar. This is the Transcar yield surface, and we see from here we see the difference between the Van Mies yield criteria, and we can say that the Transcar yield criteria is more conservative. Why? Because if a material goes to this point, then based on the Transcar yield criteria, the material has yield. But based on Van Mies stress is within the circle, therefore it has not yield. Therefore, the Transcar compared to Van Mies criteria, the Transcar criteria is more conservative. Okay. Sometimes you can use one criteria to replace the other one. You can use one instead of the other one, but the Transcar is more conservative. So now let's have a look the comparison between these two yield surface. Okay, the yield condition is independent of hydrostatic stress. Is independent of hydrostatic stress. So this is referred to these two yield criteria, which means if you put a material to put a ductile like metal deep in the sea, and it will not yield. It will not reach the yield criteria. And the Transcar yield surface is circumscribed by the Van Mies yield surface. Therefore, the Transcar criteria is more conservative. So we already mentioned, we already explained why it is more conservative. So this is the plot of those two surfaces in a three-dimensional coordinate. So we have the principal stress, we have the three principal stress, and then we plot the Transcar yield surface, and we plot the Van Mies yield surface. So the circle, the cylinder is the Van Mies the yield surface, and those this what's it called? This is the curve. Those is the Transcar yield surface, and we say Transcar yield stress is smaller, so it's more conservative. Okay. And then the third type is the Luke-Prague yield criteria, and this is very different as the previous two yield criteria. So this is applied to the pressure-dependent material such as rock, such as concrete, such as foams. And we know the rock, concrete, they are the brittle material. So it's for different types of material. So they are brittle material, and this is pressure-dependent model. The pressure-dependent model, pressure-dependent material. Okay, and here this is the formula. So here I1 is the first invariant of the Cauchy stress. G2 is the second invariant of the derivatoric part of the Cauchy stress. And in terms of the principal strain, we can write this yield criteria as this form. Okay, and this is a plot. This is a plot of the Luke-Prague yield criteria. We say it's changing. Okay, depends on the pressure. Okay, depends on pressure. The value is changing. Okay. Then we have the fourth yield criteria. Is the more conloop yield criteria, and this is also used to describe the brittle materials such as concrete, rubber piles. Okay, and it applies to material for which the compressible strength far exceeds the tensile strength. Okay, so this is another very important sentence. If you have a material in which the compressible strength is far exceeds the tensile strength, then you should use this criteria for this material. And a typical example for this kind of behavior is the concrete, right? For the concrete, the compressed strength is very, very large, but the tensile strength is very small. Therefore, you should use this criteria. Okay, and it's most commonly used in the geotechnical engineering. Okay, so we have introduced 4 criteria, and there are more than 4 criteria in the software in the real engineer problems. And the 4 criteria we introduced, the first 2 are for the ductile material, and the third and the fourth is for the brittle material. So whenever you do your simulation in the FE software, if the material goes to the plastic deformation, you have to pick a yield criteria for this material, and you have to, whenever you pick, then you have to read the material. You have to know the mechanical behavior of the material, and then you need to judge, and you need to select the correct yield criteria for that specific material. Okay, and this is a very important step. And then we have the other criteria. So this is the maximum tensile stress. It's also for the brittle material such as rock and pile, but the disadvantage is the second and third principal stress are not considered. Okay, just for you to know. Then we have some plastic mechanics. Okay, this is the knowledge from the plastic mechanics. So we have the plastic flow rules. Okay, the plastic flow rules is used to describe the changes of the plastic stream when the plastic behavior occur. Okay, so in the previous slide we said we talk about how do we judge the material has passed the critical plastic value or not. So when it passes the critical the yield strength, the plastic yield strength, then we have to define the behavior of this material in the plastic part in the plastic region, and this is what we do here. So the plastic flow rule is to describe the change of plastic strain when the plastic behavior occurs. And the plastic strain changes along the normal direction of the plastic function. And here we have the formula for the plastic strain, the changes of the plastic strain. So in this formula, d epsilon is the increment of plastic strain, d lambda is the plastic multiplier, and q is the plastic potential function. Okay. And then we have what we call it the non-associated flow rules. So when the plastic potential and yield function are different, so when these two variables are different, then we call it non-associated flow rule. Kind of they are decoupled, and this flow rule is applied to the soil and the granular material. And in comparison, we have the associated flow rule. So when the plastic potential is the yield function, and then we call it the associated flow rule. So we have this formula, and this is applied to the matter. Okay, so you should have this clear in your mind. When you simulating matter, you should use the associated flow rules. When you simulate the soil or a different type of material, then you should use the non-associated flow rules. You don't need to remember those equations or those formula, but you have to know the corresponding. Okay, to know the corresponding. And here in this figure, the plastic strain increment vector is normal to the yield surface. Okay, it's normal to the yield surface. Now let's have a look at the plastic loading and the elastic unloading rules. Elastic, so how do we judge? How do we determine it's plastic loading or elastic unloading? So for the plastic loading, if F is the yield surface, so if they are at the yield point, and if those variables, the value of those variables bigger than 0, then we call this material is doing the plastic loading. So in the contrary, if those variables, the value of those variables is smaller than 0, then we say the material is doing the elastic unloading. And if they equal to 0, and we have two scenarios. First, for the perfectly plastic material, it is doing the plastic loading. And for the hardening material, as it's a plastic state and no plastic flow. Okay, so this is the rules. This is not important. It's only for you to understand, to know. And the hardening rule. The hardening rule is important. Okay, the hardening rule is used to describe the changing rule, like the location, magnitude, shape of subsequent yield function in the plastic deformation stage. Okay, and the form of subsequent yield function can be written as this. So in this formula, H is the hardening parameter, and it depends on the deformation history, which is a function of the plastic strain. And the subsequent yield function of ideal elastic plastic material can be written as this, and it is implied the subsequent yield function is the same as the initial yield function, so there's no hardening effect. So we use a real engineer or real we all have the experience. So when we heat the matter, if we heat the matter very harder and many times the matter becomes harder and harder. We know this, and this is how the people when they produce the sword, when they produce the product, they have to heat the matter many times. What it is doing is to increase. What they are doing by the heating process is to increase the subsequent yield function, or to increase the subsequent yield stress of the matter. Okay. And we have many different mechanical model for the hardening of the material. So the first is the isotropic hardening. The isotropic hardening. So let me say what is isotropic hardening. So so in the plastic deformation, the loading yield surface is expanding in a uniform isotropic way. So we see here. So this is our initial yield surface. So this is our initial yield. Sorry, should be here. So this is our initial yield surface, and then the dot line is the subsequent yield surface. So we can say the subsequent yield surface is expanded in a uniform, which means the distance of those are the same, in a uniform and isotropic way. Therefore, the material has gone through isotropic hardening procedure. Okay, and the Van Mises subsequent yield surface is in terms of the mathematical equations in this equation. Okay, and the material plastic modulus, the hardening coefficient, can be written as this. Okay, so the isotropic hardening rule is used for most metal material. So which means for metal, you heat it, and then the subsequent yield surface will expand. When you heat again, it will expand again. Okay, by this way we are increasing the strength of the material, and this is a very useful technique. And the second type is the kinematic hardening rule. So in the plastic deformation, the loading yield surface move rapidly and maintain its shape and magnitude. As see the figure here. This is kinematic, so it will move, but magnitudes and the shape keep the same. Okay, so we have the initial. So this is our initial surface. And after the deformation, or after the heating, then it will move. So move to another location. This is our subsequent yield surface. Okay, it's moved to another location. So we call it, this is the kinematic hardening rule. Okay, and we use the mathematics to express this procedure. And so according to the kinematic tensor, the kinematic hardening rule contains the Prague kinematic hardening rule and another kinematic hardening rule. Okay, this is if you are interested, you can read some books about those two different hardening rules. Okay, the third one is the anisotropic hardening rule. So we are considering both isotropic hardening and kinematic hardening. So it's a mixture of isotropic hardening and kinematic hardening, and it's called the anisotropic hardening rule. So we have the initial. This is our initial yield surface. It's a circle. It's our initial yield surface, and then when it goes through the anisotropic hardening rule, and then the circle is changed. Okay, it's changed. The isotropic hardening, so it's expanding, and also go through the kinematic hardening. So the location is also changed. So which means we have two stages. First, we do the isotropic hardening, expanding, isotropic hardening. Then we do the kinematic hardening, which means we move the location. Okay, so and then we call this is the anisotropic hardening. Okay, then it's isotropic hardening. So this is and then this is the corresponding mathematics, and this hardening rule is applied or applicable to periodic or repeat loading scenarios. So next we have the plastic model. We said when the material goes into the plastic stage, we have to use the plastic model to describe the plastic behavior of the material. And we have many different plastic models, and so in a FE analysis, you have to decide by yourself which one you use, and you have to check the book or to check the relevant material to decide this. So here we just introduce you different plastic model. So first, the bilinear kinematic plastic model. Bilinear means you have one linear curve here, you have another linear curve here, so it's a bilinear plastic model. Kinematic means you say this is a yield point, this is another yield point. The yield point is the yield stress is the value of yield stress has changed, so it's a kinematic, it's not isotropic. Okay. Then we have the multilinear kinematic. Multilinear, so we have several linear curves. Okay, and it's kinematic, so therefore this another yield stress is different as the first yield stress. Okay, and then the third is bilinear isotropic. Okay, bilinear isotropic. So we have the two linear line, and we have this sigma. This is same. You say this is same. This is the sigma max, and this is minus sigma max. The value are same. Therefore, it's isotropic. Okay. And then we have the multilinear isotropic. So we have three linear line, and it's isotropic. Therefore, here we have the value, and this value is same as this value. Okay. So that's why we have two sigma max. Okay, two sigma max. Okay. So these are easy to understand because we can too easy to have the mapping between the curve and the language here. Now let's go to the several other types. So we have the anisotropic hardening. Anisotropic hardening is not bilinear or multilinear, so we have the anisotropic. So we have the extension, and this is the compression, and they are different values. And then we have the Drude-Prach model, so which means we use the Drude-Prach model. So we use the shear stress, which the shear stress was the criteria for the plastic deformation, for the plastic criteria. Okay. So then we put all them together. So we have these curves. So this is a linear stage, and then the yield point. Then we have the plastic stage, and then we do the unloading, and then they have different parts. This is okay. Then this is isotropic. Okay, isotropic hardening because this value equal to this value. Then we have the kinematic hardening. The kinematic hardening, which means the magnitude is the same. The magnitude is the same, but the value is changed, which means the location is changed. Then we have the mixed hardening. We say we mixed hardening. We call it the anisotropic hardening. It's mixed of the kinematic and the isotropic hardening. Okay, so this is a very whenever you're learning the plastic mechanics, this is a very typical curve, and should understand this. Okay, then part 2, the FE analysis. We have introduced different plastic model, and then the second part is how we solve those plastic model using the FE procedure or using the FE equations. So the FE analysis of material nonlinear problems. So the idea, so these are the idea. So for small deformation elastic plastic problems, the strain displacement equation is the same as the elastic problems, but the stress-strain relationship is nonlinear. Therefore, the stiffness equation is nonlinear. And second, usually use the loading increment method to solve the elastic plastic problems. And after years, the increment loading should be decreased. So we use the increment equation for the elastic plastic problems, and the material elastic plastic behavior depends on the loading and the deformation history. Therefore, in the elastic plastic analysis, divide the loading into increments, and then in each increment we linearize the equations. we don't go through those details. Okay, we don't go through those details. You have, if you are interested, you can check the books after the lecture. Okay, these are all the mathematics here. The procedure is same. You see, you have the equilibrium equation, you have the strain displacement equation, you have the stress strain equation, and then you have boundary condition, and you have your virtual displacement principle. So these are all same as the previous lectures. And then this we are doing the FE procedure. So we do the FE discretization, and we have the stiffness equation in terms of the increments variables, and then what is the procedure for the incremental FE method. Okay, we solve those equations and then we obtain the equilibrium condition. Okay, these are all, and then we use the Newton-Raphson method to solve those equations. Okay, and then we determine the elastic plastic states. We calculate the variables, we calculate the yield function, and then we decide, we judge by the yield function. And then these are all the procedures. Okay, so again, for this part, we don't go through the details, because I know if we go too much to the mathematics, you can easily get lost. So for this part, if you are interested, please read the relevant books. Now we move to part 3. This is an example of the nonlinear material. So we talk about the visco hyperelastic skeletal muscle material. So this is the skeletal muscle. Everyone have the muscle in our body. So we talk about the behavior of the muscle and how we simulate the mechanical behavior of muscle in the FE software or in the commercial software. So in order to simulate the muscle in the FE simulations or in the FE software, we need to understand the mechanical behavior of the muscle. Usually, so we have to perform many experiment tests, or we have to know the components of the muscle in order to know its behavior. So for the muscle, first is a fiber reinforced structure. We know this is the diagram of the muscle. We have many muscle fibers, so it's similar to the fiber reinforced concrete. Therefore, we should regard, so based on this feature, we should regard it as a fiber reinforced composite. Okay, so this is the corresponding mechanical model. Second, we know for the muscle, the most component is the water, and we know the water is incompressible material. Therefore, for the muscle, it is incompressible material. So we should simulate the muscle as using the incompressible mechanical model. Okay, so this all those are the pre-required knowledge for us to establish the mechanic constitutive model. And third, it's a function of active contraction. So the skeletal muscle is a voluntary muscle, so it can generate contraction by signal of the brain. So which means the muscle can contract if our brain give a signal to the muscle, and this is a very unique behavior of the muscle, and we need also to have a function to simulate this behavior. And the fourth, the muscle is a hyperelastic behavior, which means the stress-strain relationship of skeletal muscle is nonlinear, and the linear elastic model cannot accurately describe its behavior, and hyperelastic provide the way to simulate such material. So it's for the skeletal muscle is a nonlinear. We see this is a mechanical testing. So it's when we stretch, and it's changing nonlinearly with the strain. So it's independent of loading path. Therefore, it's a hyperelastic behavior. And fifth is viscoelastic elastic. So which means if we loading the material, if we loading the mechanical muscle in different loading rates, you say we use loading in different loading rates, you get different curves. So this is we call it viscoelastic or the strain loading dependent material. So it depends on the loading rate. We need when we simulate the skeletal muscle, we have to take into account those, and which means we have to consider this effect in the constitutive relationship in the mathematical equations. But we noticed there's no material model available in the commercial software like ARPX or ANSYS. And this is very common. When you simulate a real engineering problem, you will find out, okay, there's no suitable material model in those software. So in this case, you have to use the user-defined material, the interface, to define your own material model. So all the commercial software like ANSYS, ARPX, Astana, they have provided the interface to you, to the user, just in case the material model they provide cannot meet the requirements of the user. So in this case, for the skeletal muscle, there's also no suitable constitutive model in those software. Therefore, we have to do our own coding in order to describe the mechanical behavior of the skeletal muscle. So, and here is the constitutive model we have developed, or we have used, and this is this is the mechanics. So this is we mentioned we have all those behavior, we have those all different behaviors, and then we need a mechanical model to describe those behaviors. So this is we said first is fiber reinforced. So we have fibers here, and we said it's depends on the brain signal. So we have this activation function, and it's depends on the loading rate. So we have the rate dependent function, and it also depends on the stretch. Therefore, we have the stretch function, and we have all those. And we use all those mechanical model, and then we can capture the physical hyperelastic behavior of the skeletal muscle, but we have made several assumptions. So the first assumption is the energy is decoupled into an elastic energy and a visco energy, and the matrix and the fibers have a visco response. So we have this is a fiber reinforced. So we have two parts: the matrix and the fibers. And for the fiber, we use the Hayes model to describe the mechanical behavior of the fibers. And also, in this mechanical model, we ignore the interaction between the matrix and the fiber. Okay, then we said we said it's a hyperelastic. We have mentioned for the hyperelastic, we need to work out the strain energy density function. Okay. So this is a key step. We need to work out the strain energy function, strain energy density function, and from the strain energy density function, and we follow the standard procedure to work out the Cauchy stress. And this is the constitutive relationship for the muscle. Okay, and then we need to do the coding to put them into to using the user subroutine interface to put all those formula. Okay, we have many complex formula, but it looks complex, but it's very standardized. Okay, then these are the parameters we defined in those equations, and then the next step is to do the coding. Okay, to do the coding, we implement all those formulas in the software through the UMAT, through the interface. Okay, therefore, and this interface is written by the Fortran. by the Fortran. So you see, also very important. You know how to use Fortran, how to use C, and how to use those basic language. Okay. So this is the interface, and this is like a black box, and this is the parameter passed in the box, and also some parameter passed out to the software, and you have to define some of those parameters, and then to have your own coding. And this is the how they communicate with the software. They communicate through the ABACUS. Of course, this is ABACUS, through the ABACUS IMP file. So this is ABACUS IMP file. When they read the material, when they read this command, use the material, and they say, oh, okay, this is we have to define the user material model. When they read this, and then they say, oh, okay, we have to find the user material, to find this, and then they pass all those parameters into the coding, into here, and then to do the calculation. After they finish the calculation, they pass those information back into the program and to do other calculations. So this is the communication between each other. So I have the files. If you are interested, I can send you the files. You can practice by yourself to understand all those. So this is a very advanced part. You, but it's very useful. It's very useful. I have all the data and the files. You can, if you are interested, I can send to you and to learn those. And in the end, we want to do the assessment of the developed model. So we want to check whether the mechanical constitutive model we developed is good or not. So we do the assessment. So we implement in the SDNA, and the method we do the assessment is to compare with the experiment data. So we do the experiment data, use the New Zealand white rabbit, and then we perform the same experiment using the FEE simulation, and then we see what's the comparison between the results. So we have the experiment data, we have the FEE simulation, and we have different loading rates. And we can see this is the solid line, is the simulation. Dotted line is the experiment. We can say they have a good match with each other, which means our constitutive model developed can capture or can describe the mechanical behavior of the muscle. Okay, that's the conclusion. And then we also do the assessment under the active elongation procedure, because we know for the muscle it can activate and then it deform. So therefore we divide the simulation into two stages. In the first stage, the muscle is held constant and while being stimulated until fully activated. This is the first stage. Okay, so it's held constant, therefore there's no strain, but the stress is increased. And then in the second stage, then we start to pull the muscle at different strain rates, and we compare the results, the simulation with the experiment, and we say also they have a good match with each other. Therefore, our constitutive model have a good behavior, or can well describe the mechanical behavior of the skeletal muscle. Okay, so that's all for this chapter for the material nonlinear problems. So I say it again. The material model is a very, very challenging part, and very, very difficult in the FE simulation. So in FE simulation, once you determine the constitutive model of the material, then others, for example, the mesh boundary condition, should be easy to do. So, and for this part, if you have to For better understanding, you have to read more on the books and to have more knowledge. Okay, thank you very much. I'll see you next time.